Hello and welcome to the Tentative Tutor channel. Can you solve this problem in positive integers? When is a cube the sum of two squares? I'll solve this problem in 3, 2, 1. Let's first try some examples. How about x and y equal to 0? Clearly 0 squared plus 0 squared is 0 cubed, so that works. What about 2 and 2? 2 squared plus 2 squared is 2 cubed. So that also works. What about x is 2 and y is 3? We see that 13 is not a cube, so that doesn't work. We'll work in the ring of Gaussian integers. C adjoin I. That is, all numbers of the form a plus bi, where I is the square root of -1. And then keep in mind that I squared is equal to -1. So if we can write x squared plus y squared is z cubed, we can factor the left side in z of I as a product of conjugates. So the conjugate of x plus iy is x minus iy. Now we have Fermat's Christmas theorem. That is, a positive integer n is the sum of two perfect squares if and only if, in its prime factorization, it contains no odd exponent on any prime that is congruent to 3 mod 4. Like 7, 11, or 19. Suppose z cubed is the sum of two squares, and let p be a prime factor of z congruent to 3 mod 4. That is, it leaves a remainder of 3 on division by 4. Let's say its exponent is e. Then the exponent of p in z cubed is 3 times e. If e is odd, then 3 times z is odd. So that gives that we can always write z as the sum of two squares, say a and b. So if z cubed is a sum of two squares, then so is z. So by Fermat's Christmas theorem, we can always find an a and b for which z is equal to a squared plus b squared. We're once again factoring a squared plus b squared in z adjoin I as a product of conjugates, a plus bi times a minus bi. Algebra alert, coming soon, heavy algebra on the way. Buckle up, we're about to do some serious algebra. We have z cubed written as a product of conjugates, and also z. So we can write z cubed as x plus iy times x minus iy. But z is a plus bi times a minus bi. So that's a plus bi cubed times a minus bi cubed. If we then equate the left and right side factors, this will give us infinitely many solutions for z cubed equal to x squared plus y squared, but not all of them. So this assumption is just one possibility connecting x and y to a and b. Next, we can use the binomial formula to multiply out the terms in a plus bi cubed, and this is what we get. Now we can simplify by applying the fact that I squared is equal to -1. And then let's separate the real and imaginary parts. So now we have two complex numbers that are equal. That means we can equate the real and the imaginary parts. So that means x must be equal to the real part on the right side, and y must be equal to the imaginary part. And this gives us x and y as a function of a and b. So far, this is what we have. X, y, and z are parameterized by two variables a and b. As it will turn out, putting in any integers for a and b will lead us to a solution, for which z cubed is x squared plus y squared. Now let's verify that if we have x, y, and z parameterized in this manner, for any a and b, we'll get that z cubed is x squared plus y squared. Let's substitute our expressions for x and y in terms of a and b. If we square x, we get the first term, and if we square y, we get the second term by simply applying the formula for multiplying binomials. Then distributing the a squared on the left and distributing the b squared on the right, we get this expression with 6 terms. When we combine like terms, this is what we get. But we can simplify this expression a little further. Glancing at it for a bit, when we'll realize that it's actually equal to a squared plus b squared quantity cubed. You can check it by just applying the binomial formula. But a squared plus b squared is z, so it is actually equal to z cubed. So we verified that we actually do get x squared plus y squared is z cubed. So every pair of integers a and b will give rise to a parametrized triplet, x, y, and z, for which z cubed is x squared plus y squared. And then conversely, if we know z cubed can be expressed as a sum of two squares, by Fermat's Christmas theorem, we can find an a and b for which z is a squared plus b squared. And then we showed our parameterization will give us an x and y in terms of a and b, for which z cubed is x squared plus y squared. But it does not give us all representations as z cubed as a sum of two squares, as the following example shows. Let's choose a equal to 2 and b equal to 1. What we get for x is 2 and y is 11, and then z will be equal to 5. And in fact, we can check that 2 squared plus 11 squared is 5 cubed. But there's another representation of 125. That is 5 squared plus 10 squared. Now here's a small table of the triples we get for small values of a and b. Now here's our bonus problem. Solve the equation for x. Can you solve this one? Leave your answer in the comments. And once again, thanks for watching.